Welcome back. So we had talked about the mutate function and particularly case win, and that's one of the helper functions from mutate that would allow you to build a ladder of logic to create new columns. It's very, very important that you be able to do that. So for instance, one of the examples that we have used this for in the past is historically the NIH will look at minority participants in clinical trials and kind of, let's be honest, looking back over the past 20 or 30 years in clinical trials, there have been like way too few minority participants recruited into clinical trials. So one of the things that will end up happening is people of different minority and ethnic groups will end up being grouped together, even if that's technically not, even if it doesn't really make sense to do so. So for instance, we'll have like not a large representation of Pacific Islanders, maybe not a large representation of American Indian Alaskan Natives, maybe not a large representation of Middle East and North Africa, maybe not a large representation of the Indian subcontinent versus so like South. So you've got like Indian Asia versus East Asia versus like the different areas, different ethnic groups, and different so what like different I guess racial groups, even though it's not really the case. Um, and so what will happen is you'll have a whole bunch of white people. You will have a reasonable number of Black African American people, usually not enough of that either, not enough of that group either. And then you get this sort of like depending on how the data were collected, a lot of times you'll break it up as like non-Hispanic white versus Hispanic versus non-Hispanic Black, and then everything else just goes into other. And that's one of those examples where case win would be very helpful. Again, it would be better if the NIH prioritized recruiting incredibly diverse populations into their clinical trials. It would be better for the data overall, because we wouldn't be sitting here worried and be like, okay, well, yeah, we figured out that this drug works for white people. Does it actually help anybody else, though? Who knows? We don't. So, yeah, but that's on the NIH that it took them so long to really start prioritizing recruiting participants from diverse racial and ethnic backgrounds. But it's a pretty standard example of using case win, where we'll have to build out race and ethnicity categories for historic data, simply because we have to collapse a lot of participants into other racial categories that they probably wouldn't have picked for themselves. But just simply we can't do an analysis on two people. If we got a clinical trial with 1,000 people in it, we can't say, oh, let's take a look at all of the people who identified as this particular racial subgroup, because you'd have a sample size of two. You can't do any statistics with that. So more examples. So we talked about case win. More examples here. Obviously, we've got stuff like basic arithmetic. And notice here, we've got an expression over here. So I'm going to go back to this idea. This is fully formed R code. Now, it would error because R doesn't know where this object distance is. It's finding the object distance inside of the flight's data set. But if you had made R aware of where the distance object came from, this would be fully functional R code. This is called an expression. So the mutate command again works with expressions, just like the case when command did above. And so also remember, we're using this keep equals none argument. This is the shortcut for mutate then select, just to take a look at the value. Obviously, we would want to have that included on the other side. So this is the way that we would use arithmetic to find like how much different is this flight from like an average. And so the next step we could do is say maybe, okay, wrap this in parentheses and then divide by the standard deviation of flights to find, the standardized difference of flights. Or a standardized score of flight distance. And and again, so I'm going to talk about like if we wanted to add an indicator for long flights, this requires some domain expertise. So I had to go do some Googling, and they said that like for instance, this is American Airlines. This is a long flight. It's anything over 4.5 hours. And so we say, okay, well, every flight from New York to Honolulu is automatically going to be long. That doesn't make a whole lot of sense to include this in our analysis because Hawaii is not part of the continental United States. It's just so far away. So let's discard stuff that's going into Honolulu. So that's our filter here that says, give me the records that are not where the destination is not Honolulu. Then and then realistically, I probably should have removed Anchorage as well because this is also not part of the continental United States. But again, this is an example. So we're going to take our flights and then we're going to create, so that's this mutate command, we're going to create a new column called long flight, and that will be a simple check. This is going to be a true or false that is the airtime greater than 270, which is 4.5 times 60. And realistically, I probably should have written 4.5 times 60 because that's making the code easier to read. Anything that you can do to make your code easier to read is you yourself, when you come back in a couple of weeks or a couple of months, are going to thank your past self for making your code easier to read. And so back here, and then remove all of the records where people were where the flights were going to Honolulu, and then reorder the columns. Okay, so I'm using the everything command. So I want to keep all of the columns. Notice I have 20 of them now because I have a long flight indicator. So I had 19 columns originally. I've just added one. But I want to reorder the columns so that the destination, whether or not it's a long flight, and the airtime comes out first. So we're seeing here that New York to LA, 440 minutes. New York to, I'm assuming that's San Francisco, 438 minutes. Another flight, maybe to SFOs, maybe San Francisco, 490 minutes. Don't know why this one was much longer than the other flights to San Francisco. Who knows? Maybe there's some weather or something like that. And then so right here, we're reordering the columns, and then, so remember pipe operator is red, and then we are going to arrange the airtime descending. So these are the longest flights are going to be up at the top, and then and so down at the bottom, we should see all of the flights that are closer to 270 minutes. And we see here, to be honest with you, we started off with about 370,000 rows. We have like 336,000 rows. So most of the flights out of New York would be considered by American Airlines to be long flights. That's kind of interesting. And this is, yeah, something about like how travel happens in the United States, that we use these travel hubs where basically if you're in smaller cities, you'll fly to a larger city. And then from that larger city, you'll fly to another large city. Like you're not going to fly directly from Rochester to Los Angeles. You're going to fly from Rochester to New York and then from New York to Los Angeles or something like that. And it's just, I think it's kind of interesting that gets into like the logistics of flights. This is an optional section, so I'm just going to kind of brush over it. Because it deals with modular arithmetic, which many of you have never seen modular arithmetic before. So I want to at least talk about it a little bit. And I'm going to talk about the modular arithmetic operators here. So this thing right here, this crazy double percent sign is called the modulo operator. If you are interested in this, I recommend that you go at least breeze through this article, kind of understand a little bit of the high points. It's sometimes called the remainder operator. So this is so A then modulo B. So it's read A modulo B returns the remainder after dividing A by B. Why would this be important? So notice here that the departure time, it's read as like a human time. So this means 5:17. So this is 5 hours and 17 minutes after midnight. This is 5 hours and 33 minutes after midnight. This is 5 hours and 42 minutes after midnight. This is not 517 minutes after midnight. Okay, so it's very important that if you tried to do math with this column, you would fail spectacularly because these are not actual numbers in terms of base 10 arithmetic. This is actually a like, so this 5 is like a base 24 number, and then this 17 is a base 60 number. We can't add and subtract numbers like this. We can't just be like, oh, well, what's 517 minus 430 or something? That doesn't make any sense. Now we know that 517 minus like 430, the time between 4:30 in the morning and 517 in the morning would be 30 plus 17 or 47 minutes. But 517 minus 430, well, if we do that with math, if you will, so 517 minus 4:30, this is not going to be 47 minutes. This is going to be 87 something, but it's not a minute anymore. Because the units here don't make any sense because the 5 is out of a base 24 system, so there's 24 hours in the day, and the other two numerals, these are out of a base 60 system. So this is not anything that we can actually do math on. So if we needed to do math on this, then we would actually have to create a new column called the departure time in minutes, and this is going to be the minutes after midnight, and then the arrival time in minutes is also going to be the minutes after midnight. So the way that we would do this is we would try to just look at the hundreds place column, and so we're going to use this integer division operator, and that's this one right here, and that basically says if I take 517 and do integer division divided by 100, it's going to return 5. And it's just asking the question, how many hundreds are there in this number? There are 5 hundreds in this number. So these are the hours, and I'm going to say, okay, give me the hours right here. That's how many hundreds there are. Multiply this by 60, so that gives me the actual hours. And so this is 317 minutes after midnight. And we can confirm that. We can say, okay, so what's 317? Actually, I'll just go to Wolfram Alpha. Wolfram Alpha. And I say 317 minutes after midnight. And it should be 5:17 in the morning. And it is 5:17 in the morning. By the way, if you've never seen Wolfram Alpha before, highly recommend it. It's pretty great. So, but anyway, so this is, now I can do math on this. So if I had found a flight that was 4:30 in the morning and I said, okay, I want to find the difference between the flight that left at 5:17 and the flight that left at 4:30, like what's the difference in the departure times? I can do math on this column because this column is an integer count of how many minutes it's been since midnight. I'm allowed to do math with this. I cannot do math with this. Okay, this is I cannot do standard arithmetic with standard. Well, let me clarify this. I cannot do standard base 10 arithmetic with this column. Does not work. I can do standard base 10 arithmetic with this column because now I'm counting in base 10 the number of minutes since midnight. So anyway, like I said, this section is optional. You don't need to learn this, but if you've never seen the integer division operator, or if you've never seen the modulo operator, I would say at least just be aware that they exist. They are useful tools to have whenever you're writing computer code. So that'll be the end of this section, and we'll pick back up next time with the summarize command. So we'll group by and summarize, but really just the summarize command because you're not ever going to use group by without it. Okay. All right. See you next time.